Okay guys, in this video lesson we're going to do a little bit of information on conservation of energy. So here we go. First thing we got to do is review a little bit about kinetic energy. Okay, so recall that kinetic energy is energy that's moving, and the faster something moves, more kinetic energy you have. The more massive it is, the more kinetic energy it has. So if we recall, we have our equation for kinetic energy. That kinetic energy is 1/2 the mass times the velocity squared. Okay. So one piece of the puzzle for conservation of energy is what is the kinetic energy. So that's one quick review. Another quick review is looking at potential energy, gravitational. Okay, so gravitational potential energy, remember, comes from height. So the higher we are, the h here, the more gravitational potential energy we have. Remembering about g and then the mass of the object also. Okay, so this is always our energy due to position. So these two equations are review ones. We do have a new one that we need to talk about because not all potential energy is due to position. Some potential energy comes from elasticity, or some potential energy comes from stretching or compressing things. Okay, so if we can store energy when we put a stress or a strain on something, that's called elastic potential energy. Okay, so imagine taking a rubber band and pulling it and stretching a rubber band, or imagine taking a spring and compressing a spring. We are essentially doing work on that rubber band or work on that spring to change its position, giving it a strain or a stress. That strain or stress now has potential energy to release. Okay, when we do that, we actually have this equation. Now, it should look kind of familiar to you because when we release elastic potential energy, we get a movement from that. So it should make sense that the equation looks something similar to our kinetic energy equation. Okay, so let's go through the components of this. So the potential energy we get from elastic expansion or contraction, or a stress or a strain, is 1/2 K. Okay, K is the spring constant. Okay, so this is basically how stiff the spring is. Okay, so think of like slinkies, like those little toys you had as a kid. They have really low spring constants. Okay, so the force they can apply in newtons per meter of distance to stretch them or compress them is very weak. Okay, think of like your car struts or springs on like heavy equipment. Those K values would be very high, okay, because the force that they can require to stretch or to compress them would be really high, okay. So K is basically how stiff the spring is, okay, and then X is how far you move it, all right. So every spring has a natural position where if you leave it alone and have no stress or strain on it, that spring is just going to sit there and be no energy to it at all, okay. Once we stretch or compress that spring, that's our X, okay? It's kind of like displacement, where we use X as in our displacement, very similar. So you stretch the spring 2 centimeters, or you compress it 2 centimeters. That's what we're talking about here, okay? We do want to measure this in meters. So if you take a look, our units here are newtons and meters again. But it is often that when we talk about X, that we say centimeters, because if we're dealing with small springs, in small movements, it's more common that you might see it in centimeters and have to convert to meters as you do that, okay? So one new equation for us where we deal with that. So let's do a little practice problem on the board just to kind of get an idea how that would work, okay? So let's say I had a spring and it's some sort of spring, and on the end of it I have a block, okay? If I were to compress this spring, so I compress it a distance from here back to here. Let's say I compress that 12 centimeters, okay? So if I compress that spring 12 centimeters, and if the spring constant for my spring is equal to, let's say it's not a very strong spring, let's say it's like 25 newtons per meter, okay? So if I have a compression of 12 centimeters on a spring, and I have a spring constant of 25 newton meters, okay? How much, or basically what amount of potential energy, elastic, did I create? Okay? So how much elastic potential energy did I create? Well, let's start our equation up. So our potential energy elastic is equal to 1/2. Okay, K, and K is our spring constant, so it would be 25 newtons per meter times how far we stretch it squared. So this would be our X. So it's 12 centimeters or 0.12 meters squared. Okay, so we take 1/2 times 25 times 0.12 meters squared, and what I get is 0.5 times 25 times 0.12 squared. And the energy I get in this is 0.18. And take a looking at our measurements, I have meters squared over meters, so one of my meters cancels out, and my potential energy, again, is going to be back into Newton meters. Okay? So essentially, by compressing this spring 12 centimeters, if it has a spring constant of only 25 newtons per meter, I end up getting a potential energy gain of 0.18 Newton meters. Okay? Which also means the work required to do this. So if I actually took my hand and I pushed this in, the work that was required for me to actually make this happen would be 0.18 Newton meters, because the potential energy gained would also equal the work required. Go back to our work energy theorem from last unit, where the work put in, okay, is what we get out of it. Now, once we release the spring, if I let go and let this thing shoot back out, it's going to do that much more work on this block, okay? So if we know the mass of this block and we know that the potential energy it has, we have the potential to be able to solve for how fast we can release that block, or how fast that block will be moving once we let go of it, in terms of conserving our energy, okay? So that's elastic potential energy. It's just a function of how far you stretch a spring compared to how strong the spring is, okay? Now, dealing with mechanical energy in general, okay? So when we're looking at conserving energy, we want to be able to focus on all the different parts of energy that are available, which means that the mechanical energy that is present in any system or substance is its kinetic energy plus its potential energy, okay? So you add those two up, that gives you mechanical. Now remember, there are two types of potential energies now. So what happens is the equation gets a little more complex. We say that mechanical energy that something has is equal to its kinetic energy plus its potential energy due to position plus any potential energy due to its elastic scenario, okay? So it's potential, see how I use that word? There's potential that there's three different types of energies present. Now the trick is, this total energy, the mechanical energy here, is always the same, okay? So we don't ever gain mechanical energy, we don't ever lose mechanical energy. This number stays constant. It's just a switching between these three variables as the object moves and shifts and changes position, okay? Now, when we conserve mechanical energy, things that we got to make sure that we always are keeping track of, okay? Total amount of energy is constant. The type changes. Again, total remains the same. I've said that like 5 times now, okay? So total energy stays the same, all right? If something is falling, okay, let's take a look at that. If something is falling, let's do something simple like a diver off of a diving board. So if we have a person who's going to fall off a diving board, and they just step straight off the board and they start to fall, okay? As they fall down, okay, let's talk about their energies, okay? At the very top, right here, all their energy is potential energy due to gravity, okay? That's all their energy. But as they fall, their potential energy due to gravity is going to decrease. Because as they fall, what's happening to them? Well, as they fall, they're accelerating. And as they accelerate, that means they're gaining kinetic energy. So the kinetic energy they have will increase as they fall, okay? At the very bottom of the fall, the instant at the bottom, right here, not after they hit, not after they've slowed down, The second they finally just touch the bottom, all of your energy is going to be kinetic. Because if we consider this our 0 point for 0 height, you'll have 0 potential energy due to gravity at this point here. Okay? So as something falls, it's going to be increasing kinetic energy, it's going to be decreasing its gravitational potential energy. So if this goes down by 5, this has to go up by 5. This goes down by 10, this goes up by 10. It's proportional between the two things, okay? So think about it. Halfway down, if you're halfway through your fall, half of your energy is potential, half of your energy is kinetic, okay? Now, same idea if you're stretching or compressing, okay? If I have a spring, and let's say I hook a spring to a stationary object, and I have a mass of that. And I pull this spring downwards, okay? As I pull this down, okay, I'm gaining, or I'm increasing potential energy due to elasticity, okay, as I pull that down, okay? As soon as I let go, the spring will shoot back up, and I'm going to lose that potential energy due to elastic, okay? So the spring is going to have 0, if it's at its natural position, its potential energy due to elasticity will be 0. Anything off that natural position is going to have some elastic potential energy. So if it comes up and it compresses the spring, so the block comes up high, and we compress the spring like this, that compression that happens also will give it elastic potential energy. So springs can both be compressed and stretched, okay? So anything off of its natural position, where it has 0 potential energy elastic, we have some sort of potential energy that's elastic to it, okay? Which means as something moves or stretches or changes, we can compare the initial mechanical energy to the final mechanical energy, okay? So we know that the initial mechanical energy has to equal the final, which means all the kinetic energies plus the potential energies have to equal the final kinetic energies and the final potential energies. Which means, and here's where it gets really fun, breaking it down across the board, that your kinetic energy initial plus your gravitational potential energy initial plus your compression or potential energy of elasticity initial has to equal all your finals, okay? So if you take a look, the equation gets really long really fast, okay? However, most of the time, we're looking at things that either start in their natural position, or they're going to start by not moving, or they're going to start by hitting, or they're going to end by hitting the ground, so they're at the bottom of a fall. So one of the things you really want to look for in these kind of problems is which of these variables can I make 0, okay? So if there is no spring, if there's no stretching, if there's no elasticity, this whole piece disappears. This whole piece disappears. If it's only a spring and there's no height, this whole piece disappears, and this whole piece disappears, okay? So keep in mind that most of the time for mechanical energy problems, even though this looks really long and complex, most of the time there are at least 1 or 2 of these that we can make 0 and get rid of them right away from our problems, okay? All right, so we're going to end here, and then in class, we're going to start talking about conceptualizing this, okay? All right, guys, that's it for the video lesson. We'll come back to class. We'll start with this, and then we'll do a lot more practice with this, giving you guys the confidence you need in terms of both conceptually understanding this and mathematically solving for these. Thank you.